This video is going to finish up our techniques of integration. I'm going to start by showing you just a couple little tips and tricks you can use for some other strategies we've already done. And then I will proceed to the last strategy of integration, which is referred to as integration using partial fractions. It's a nice strategy that most students enjoy just because it is very structured as compared to some of the others that are a little bit more puzzle-like. Okay, so I'm going to start and go back to integration by trig substitution. And I've got a couple of examples here that at first glance, you would probably question whether they actually are integration by trig substitution because they don't quite suit the pattern of what we're used to looking for. So this first one, for example, when I look at this, it doesn't look like that pattern we're used to seeing of something like, just give you an example here. Let's say I had the square root, and then I had dx. That's a bad interval, but let's see, there, yeah, that's perfect. Your Pythagorean, you set up your two sides in your triangle, and away you go. Well, this doesn't look like what we're used to seeing. However, it is one of those special cases that sometimes has just a little extra hiccup to it. And of course, we know, as you've done enough math now, that often happens. So in the title of this, it tells you sometimes completing the square can be a useful strategy. Well, I'm going to show you what that means and how that works. So I look at this, and it's not du over u. It's not the strategy I'm going to show you a little bit later on probably would get you through this one, but it's not a trig substitution. It's not a chain rule. It's none of the things that we've looked at up until this point. So what I'm going to do is take the denominator, and I'll refresh your memories on how to complete the square. So I'm going to take x squared plus 10x, put a plus sign, leave some room, put your plus 41 back, and then hopefully this will refresh your memory on how you complete the square. So you always want to have a 1 as a coefficient here, which I already have. Once you have that, you're going to take half of the middle term and square it. So half of 10 is 5. 5 squared is 25. You've added 25. That means you have to subtract 25 at the end. That's going to generate x plus 5 squared plus 16. So the question now is the integral of dx over x plus 5 squared plus 16. And now it actually is the pattern of a trig substitution because you have this x plus 5. Now, this is the first time you've seen this, but one of your sides could be, rather than just a single variable, could be x plus 5, and then your other side could be 4. So I draw my triangle out like so. Right triangle. So these would have to be the two legs because they're at it. So one side's got to be x plus 5. The other side's got to be 4. That would make the hypotenuse x plus 5 squared plus 16, which you can see is getting close to because this is now this expression down here. All right, so let's rewrite this question now. Oops. So now it's going to be, I need some substitutions. So let's call this our angle theta. Let's start with a nice easy theta to get, or an easy trig ratio that will give us dx. I'm going to go with tangent of theta. So the tangent of angle theta would be x plus 5, the opposite, over the adjacent, which is 4. Just going to rearrange this. 4 tan theta is x plus 5. Take the derivative with respect to x, both the left and right side. So you're going to get 4. Derivative of tangent is secant squared theta, d theta over dx. The derivative of x is just 1. Multiply both sides by 4 secant squared theta. D theta would be equal to dx. So I'm going to put this in the numerator rather than dx. Now I'm also going to need something to put for this. So I want to involve my hypotenuse, and you can see that. And I don't want to use this side. I want to use this side here because I don't have just a constant. So I'm going to go with, just put it over here. Let's go with, I want to get this in the numerator and this in the denominator. So I'm going to go secant. Secant of angle theta is x plus 5 squared plus 16 over 4. So now I need something for just this, no radical sign on it. So you could square now. I'm going to just rearrange a little bit here first. So I got 4 secant theta square root x plus 5 squared plus 16. Square both sides. And now I've got a trig expression that I can put in there to represent this piece of my integral. So we'll rewrite the integral and see what we've got. And those of you that are following along and getting the hang of this, you'll see this is going to work really nice. Dx is 4 secant squared theta d theta. This expression, there it is right there, is equal to 16 secant squared theta. Well, that couldn't work any better because look at that. Those are gone. 4/16 is just a constant, 1/4. And all that I have left is d theta. Well, the integral of d theta is theta. And don't forget, you got to go back now and get a trig ratio that you could use to represent theta. So I'm going to, I'm going to use the one I had earlier, tan of theta. So I'm just going to go 1/4 inverse tan of x plus 5 over 4 would be a representation of theta, and then plus c. And there you have it. So that was an example where completing the square allowed you to come up with a trig substitution. So it didn't appear to be a trig substitution in the beginning, but the fact that it was that nice trinomial that we're used to going through and completing the square where you have something in brackets squared plus a number, well then all of a sudden that will, this could be a minus as well, then that would work well to set up a trig substitution. All right, I'm just going to go through the one example to show you how that works. There is another one here you could try on your own if you like, but I'm just going to show you the one so you see how that works. All right, I have one other little tip that I want to show you. So this is not really considered an integration strategy per se. It's just a little tip to watch for as you're doing an integral. And the way it works, we're going to use long division. So hopefully, way back in pre-calc 12B, I think it was, when we did polynomials, and we looked at how to divide polynomials, you can recall how that worked. And you'll see a couple of examples here where I'll show you. And the way you determine whether this would be a good idea is looking at what's called the degree. And the degree is just the highest exponent that you see anywhere in the polynomial. This one is degree 3. This one is degree 1, because the highest exponent up here is a 3. Highest exponent here is a 1. This would be degree 3. This would be degree 2. Okay, so just before I do that, I just want to show you my page for a sec. If we had, I don't know, 37, and we divided that by 5, well, we'd say it goes evenly 7 times, giving me a 35, and I would subtract. Well, that means that 5 goes into 37 7 full times plus this many fifths would be left. So it's really 7 2/5. If I went, which if you think about it, 37 over 35, so just simplifying fractions, it is, oh, not 35, sorry, 37 over 5, which is what I started with. 37 over 5 is 7. 7 times 5 is 35. That means there's 2 left over. It's 7 2/5. So if I took x squared minus 3x plus 2, and I divide that by x minus 4, let's say. X goes into x squared how many times? We would say just x. That would give me x squared minus 4x. Subtract, give me 0. Subtract, give me a positive x, because it's -3, subtract a negative, so that's positive. Bring this one down. X goes into x plus 1 times. Multiply that. Subtract, you get 2, take away a -4, you get 6. Now, using what we did over here, this means that if I had x squared minus 3x plus 2, and I divided it by x minus 4, the answer would be x plus 1 plus, so right, that's like your answer here, plus there would be 6 left over of these. Like here, remember I had a 2, so that meant it was that answer, so went that many times evenly, plus there were 2/5 left over. So it goes this many times evenly, plus there is that over that left over. So if you had this expression and you were taking the integral, this is another way to write that, which would probably be much easier to integrate than the original expression. Oops, sorry. So backing up to here, if the numerator is the same degree or higher, long division is always going to be a great first step to make things easier. I'm not saying it's the only way to do it, but it can certainly be a very time saving and get you going in the right direction if you're stumped. So I look at this one, I say, oh, this is a higher degree. So I'm going to take x cubed plus 4, and I'm going to divide by x plus 1. So remember how this works. Just look at the first term only. How many times does x go evenly into x to the third? X squared. Multiply these two together, and you'll get x cubed plus x squared. Subtract. So those are gone. Now there's no x squareds here, so it's 0x squared minus x squared. So that's negative x squared. Let's bring down the plus 4. If you have 2 terms here, you want 2 terms here. Start again. What do I multiply x by to get negative x squared? It would be a negative x. That will give me negative x squared. Take away x. Subtract. Those are gone. So those are the x squareds. The next would be the x's. Well, I don't have any x's. So 0x minus negative x. That's positive x. Bring your plus 4 down. X goes into x plus 1 times, leaving me with x plus 1 here. Subtract, those are gone. 4 take away 1 is 3. Now, here's the new question. I'm just going to write it here. I'll move that one down later. So the new question would be, goes evenly this, so this divided by this is the same thing as this plus this over this. Now, if you because these are all added and subtracted, you could simply think of this as the integral of x squared minus x plus 1, which is just 3 power. I'm doing 3 power rules, plus 3 times the integral of just dx over x plus 1. And the nice thing is when this is linear, it's just du over u. So this is natural log. So now an integral that looked quite complicated in the beginning has now turned out to be, here's our final answer, x cubed over 3 minus x squared over 2 plus x plus 3. Because this is the pattern du over u, it is natural log of x plus 1 plus your constant c. Okay, so I got another example here. I'll take this one, do it on a clean page. Okay, so same type of deal. The numerator is a higher exponent or higher degree than the denominator. Let's do a long division, chop it up and make it a little bit easier to manage. I'm going to take the numerator and I'm going to divide it by the denominator. All right, x squared, I want to get 3x cubed, so I'm going to multiply it by 3x. That will give me my 3x cubed plus 12x. Subtract, those are 0, 2, subtract 12, that's negative 10x. All right, so as soon as I see this is a lower exponent, so it's exponent 1, I was dividing by an x squared, this is all considered the remainder, this whole thing down here. So this integral will be changed to 3x plus this over this dx. Now, this one's still not going to be better than it was, but it's still going to be a challenge. I'm going to, this is fine. That's all good. This isn't du over u, and it's not going to follow that pattern. So this is one where I would suggest splitting. I think we've referred to it or talked about it earlier. Splitting is when you've got something like this, a plus b over x down here in the bottom. Well, then you just put a over x plus b over x. It would be equal to the same thing. Now, students will then try and split that. You can't split the denominator, but you can split a numerator like that, because if I had a over x, so think of numbers, if you had 3/4 plus 1/4, well, you leave the denominator and the numerator stays. You just add those together. So I could just work backwards and split that off and say 3/4 plus 1/4 would have been the same thing as 4/4. So here, I'm going to split this. I'm going to write it as negative 10x over x squared plus 4. Hopefully you notice that this is the pattern, not quite, but it's close to du over u. Only thing wrong is the constant in front. So remember, you can always adjust constants. Now, in the last assignment, we ran into a situation where there's a couple instances where students are trying to put variables in here that are missing. You can't adjust variables. You can only adjust constants. All right, so I can fix that. And then I'm going to have here plus 5 over x squared plus 4. And then all of that dx. Okay, so let's continue chopping away here. I'm going to basically look at now 3 intervals. So I got the interval of 3x dx. Easy. Let's put a minus here. 3x dx minus, let's just for this minus, put the 10 out in front, x over x squared plus 4 dx. This one I can do by simply putting a 2 there and a 2 there. Now it's the pattern du over u, natural log. So 2 of them are ready to go. This is just power rule. That's easy. Now this one is not du over u, but it is following that pattern of trig substitution. So I'm going to take that 5 over x squared plus 4, and I'm going to set that up on a triangle. So let's do that. Let's come over here. Let's make a triangle. These would have to be the legs, x and 2. That would make this side x squared plus 4 square root. One angle here, theta. Let's go with cotan of theta would be 2. No, I don't want cotan. Sorry, I always want my unknown in the numerator. Things will work out easier for me. So I'm going to go with tan of theta, which will give me x over 2. 2 tan of theta is x. Take the derivative. I'm trying to get a substitution for dx. 2 secant squared theta will be, oh, forgot my d theta. D theta would have been d theta over dx. This would equal 1. Multiply both sides by dx. So there's my substitution for dx. So the other substitution we need is for this without the radical sign. That's okay. We set it up with the radical sign, and then we just square both sides. Let's go cos of theta. No, I want this in the numerator. So let's go secant of theta would be square root x squared plus 4 over 2. Square both sides. Or so, not yet. 2. Just multiply both sides by 2. Getting ahead of myself. Now square both sides. Okay, so we're going to use this information here. All of this, I'm just going to put a little circle around this, to rebuild this part here. So this is going to become plus, so the 5 can go front, integral. Right, so imagine that we're just doing the integral of this term, and I'm doing it out over here. So dx, I believe we said was 2 secant squared theta. 2 secant squared theta d theta. And x squared plus 4 without the radical sign on it. We had figured out that that would be 4 secant squared theta. Again, nice. Those are gone. This is going to bring the 2 out. You're going to get 10 over 4, so you're going to get 5 over 2. So let me just clean this up a little bit. Apologize, it's getting a little messy on this. This is u over u. So these two are perfect and ready to go. You could have even integrated them now if you wanted to. I'll just wait and do that all at the end. So I said I got 5 times 2 is 10 over 4. So I've got a plus 5 over 2 here. And this one, now remember, you said, why you got x's and things? This one, I'm going to get the x's back in a moment. I'm referring to them over here. I've got it into a trig substitution for a moment or two to help me figure out my integral. So it's going to be add one of the exponent, divide by the exponent. 3 over 2 x squared minus 5 natural log x squared plus 4 plus 5 over 2. The integral of d theta is just theta. So theta, go over here, find a nice easy substitution. Here's the easiest one. Let's go inverse tan of x over 2 would be equal to theta. And here would be my final answer. I'll get that pen just a second. Yeah, fix that. Sorry about that. There's a button on the pen that kind of sticks and everything goes crazy. So I've got 3 over 2. Uh-oh, maybe I didn't fix it. 3 over 2. Give me another second. Sorry. Okay, technical glitch seems to be fixed. Here we go. 3 over 2. So I said this is 3 over 2 x squared minus 5 natural log x squared plus 4 plus 5 over 2. Now you can't have thetas and x's mixed together, so you're going to now go to here, as I said, and I'm going to use this one. So theta would be the inverse tangent of x over 2 plus c. And again, as I mentioned when we did trig substitution, there's 5 other things that students could have that would be correct. So if you look at an answer key and you did not see this, it doesn't mean necessarily that your answer is not correct, because they just might have picked a different inverse trig function to represent theta, because there's always 6 options. Okay, so that is an example where long division. Now that one was still a challenge, as I said, but as I've stated before, when you get to this point, these become very much a problem that you just got to kind of keep wheeling your way through. Sometimes you try things that don't work. Maybe say, oh, I forgot about the dividing by the highest power. There's a lot of things I know you have to keep straight. That's why people love mathematicians, because you guys have minds that can keep all this stuff straight and figure it out. All right, here we are at our final strategy of integration. Well, what I want to do here first is go through. It's basically undoing finding common denominators, and the process to do that is called partial fractions. So I'm just going to show you or refresh your memory on how you get common denominators. So if I had these 2 fractions, the common denominator would be the product of x minus 5 multiplied by x plus 4. And the way it would work is you'd look at this denominator and say, well, if I want this denominator to become this, again, same numbers, if you have 1/3 plus 3/5, and the common denominator is 15, well, the way you figure out the numerator is you say, what do I have to multiply the denominator by to get that? Well, in this case, it would be times 5. So you have to multiply the numerator by 5. That shouldn't be there. Then you'd look at the other fraction, which is multiplied by 3 to get 15. Well, that means you got to multiply the numerator by 3. And you'd end up with 14/15. Okay, so we're going to go through. Now, so over here, as I said, these 2 are multiplied together, so now we just apply that same idea. So to turn that denominator into that, I would have to multiply the numerator by x plus 4 plus this denominator to become this, I would have to multiply by x subtract 5. Leaving me with 3x plus 12 plus 2x minus 10 over this. And that would then be 5x plus 2 over, if I actually multiply those out, x squared be plus 4x minus 5x, so minus x, negative 5 times 4 minus 20. So I started with this, and I turned it into this. I just want you to think about integrals. If this was your original question, right here, versus this instead, wouldn't this be a lot easier to do? Because now it would just be du over u, du over u. You get 2 linear factors down here, so your derivative is always just some constant. In this case, it's really easy because it's just a 1. So if we could learn somehow to take this process that got us to here and basically undo it and get back to here, it's going to be a technique of integration that will turn this type of situation into a more manageable situation. And it's called partial fractions. All right, so what we're doing, as I said, it's called partial fractions. So what I'm going to do is show you how you undo this. And for the most part, it's fairly straightforward. Can get a little time consuming, but other than that, works quite well. Okay, so imagine we started with this. I'm just going to I'll outline it here in the first example, and then we'll do a few examples of this. So you always are going to want to factor the denominator. Don't worry about the numerator, just the denominator. So the denominator is factored. Then you're going to separate it into what are called partial fractions. You're going to take each factor that shows up in the denominator, and you're going to just pick a letter. So usually we'll use kind of like your letters of the alphabet, A, B, and C, whatever, doesn't matter. So A over X minus 5 plus B over X plus 4. Those two, when added together, would have given you this as the common denominator. We also know that they gave us this as the numerator. So what you're going to do is now, I'll finish the rest of it out. So you're going to take your, find your common denominator, which would be X minus 5, X plus 4. This fraction, the one with the A in the numerator, you'd have to multiply by X plus 4. The one with B, you'd have to multiply by X minus 5, giving you AX plus 4A, oops, 4A, AX plus 4A plus BX minus 5B, that would be your numerator. These multiply together, and again, I'm trying to figure out what A and B must have been to give me this fraction over here, because that was the original. Well, if you were to expand the denominator, it would be already the denominator on the right side. So this is just your x squared minus x minus 20 equals 5x plus 2, x squared minus x, subtract 20. Well, in a fraction, if the denominator is already equal to the denominator, and there's equal fractions, the only way that can possibly happen is if the numerator is now set equal to the numerator here. So we're going to say AX plus 4A plus BX, subtract 5B, has to be equal to 5x plus 2. The numerator, because the denominators are the same, the numerator on the left has to be equal to the numerator on the right. Well, that means when I combine the x terms here on the left side, they've got to give me the same as the x value on this side. So I'm going to say A plus B. So these coefficients, when I add them, I've got to get that number. And when I add the non-numeric ones, so the 4A and the minus 5B, 4A and minus 5B, they have to give me the number here, because these ones don't have x's on them, so those would be your numeric terms. When I combine those two together, I've got to get that answer in order for the left side to turn out the same as the right side. Well, now at this point, you have what's called a system of equations. And your goal is to figure out the A and the B. You can do elimination, you can do substitution, any of the strategies you've acquired over the last couple of years, you're welcome to use. I think in this one, I like it's kind of nice for elimination. I'm going to take this top equation. I'm just going to multiply it by 4. 4A plus 4B equals 20. Then I'm going to subtract. So this, take away this, is 0. Negative 5B, take away 4B is negative 9B. 2, take away 20 is negative 18. Divide both sides by negative 9. And I get B is 2. So I know that the B value is 2. Find the easiest equation you can, that'll let you get A. So I'm going to go right back to this one. A plus B has to equal 5. I now know B. So A plus 2's got to be 5. A's got to be 3. So what's A and B? I don't remember what they are. Go way back to the top. Way up here. Here's where they are. Look, A is the number over x minus 5, and B is the number over x plus 4. So we said that A, so I know that 3 over x minus 5 plus B over x plus 4 has to give me this original. Hopefully I didn't screw those up. Did I get them backwards? I have double check. Yep, really good. So A is over x minus 5 and B is over x plus 4. So here's what I now know. I started with this. I know that I could change this into this. So if this was an integral, it would now become this, which, find your dx here, and your dx here, and your dx here, which is what I think I have on my next slide. We'll just keep going here. So if that was the original question, so let's suppose I had, just because all the work's right here in this page, let's just keep going here. So if the original question was find the integral of 5x plus 2 over x squared, subtract x minus 20, dx, and it's not du over u, so it's not that nice pattern of natural log, then it's not trig substitution. I got us into partial fractions. So let's suppose you did all that work up above, which you'd have to do, and then you'd be able to say another way to write this is the integral of 3 dx over x subtract 5 plus 2 integral dx over x plus 4. This 3 here is probably better to put it out front. 3 there, and now you've got 2 natural logs. 3 natural log of x minus 5 plus 2 natural log of x plus 4 plus a constant c. So they are fairly labor intensive, meaning they take quite a bit of work to get to your manageable integral. However, they are quite systematic. Now, having said that, there are a couple little things you got to watch for, and I'll point to that's the one we just did. Okay, special situations. So really make sure you take note of these. I think there's 3 or 4 of them. This one I've already mentioned earlier. If the degree of the numerator is the same or higher, then the denominator should always do long division. So that one we've mentioned. So often, if you had this as an integral, some students would say, oh, look at that, it's looks a lot like partial fractions. You got polynomial over polynomial, which in many cases can be, but if you were to divide this out, it would make for much easier partial fractions. So instead of this, notice what it would turn it into. It would be this. Yeah, this would still be partial fractions, but this would be much easier to manage than that original one. So always divide the numerator by the denominator if the degree is the same or higher. So you have to make sure you don't forget about that. This one is, it just means that if you have multiple factors, so you got here 1, 2, 3, that means you need 3 partial fractions. So for every linear factor, linear just means the x is to the first power. So for every linear factor, you need a partial fraction. Now, that's not too exciting. It's the next 2 that you've got to really, really pay attention to. And students miss these ones. And as soon as you miss these little tidbits here, you're going to be into a mess and they're not going to work. So the first one is if you've got a linear factor that's repeated, meaning it's raised, so you say linear factor, x plus 3, but it's repeated. It's actually there squared. Could be cubed, could be the 4th. If it is, it's going to be difficult. Usually not any higher than squared, but I'll show you here. You'll get the idea of how you have to deal with it. The problem is this. If you had, I'll just show you an easy example over here. If I had 1 over x plus 1 over x squared, here's what students mistakenly do. They say, oh, the common denominator is x cubed. I say, well, it is a common denominator, but it's not the least common denominator. And they get x cubed because they just take these two and multiply them together. But you don't have to do that because x divides into x squared, and x squared divides into x squared. So the least common denominator of these two is x squared. Well, this could be x plus 1 and x plus 1 squared. And if that was the case, it would be x plus 1 squared would be your common denominator. So what you have to understand, it's kind of messy, let me just put that a little bit cleaner, is that if you have these two fractions, so suppose I have 1 over x plus 1 plus 1 over x plus 1 squared, the least common denominator is not x plus 1 cubed. That is a common denominator. That's like having denominators of 2 and 6 and using 24. That works, but it's not the least common denominator. It makes it more difficult. So in this one, if you have x plus 1 and x plus 1 squared, x plus 1 squared is your least common denominator. So the problem is if we're at this and going backwards like we're trying to learn how to do now, I have to realize that I need to account for, yes, that could have been a factor. However, x plus 1 squared would have also covered an x plus 1 factor. So look at this one. I see x plus 3 squared. So when I split the partial fractions, I need to account for x plus 3 to the 1. That could be 1. So I'm going to call it a over that. Then I have to account for the 1 squared, which would be b. And then I have my other third factor here, so it's c over x minus 2. Imagine this was, just to show you what I mean, let's suppose I had an x plus 2 cubed, and that was in the bottom of some fraction. Well, the partial fractions would be x plus 2, a over that, b over x plus 2 squared, and then there could even be a third one for x plus 2 cubed, because you have to account for every possible factor below that exponent that would have also divided into it, which is why you need to make sure you get these multiple ones. So that's when you have a linear factor repeated, which means raised to an exponent, you must make multiple partial fractions to describe it based on what exponent it is. As I said, you're usually only going to get squareds here, but in theory, I showed you this is how you would deal with it if it was to the third. All right, and the last one. The last one is when you've got everything factored out as far as you possibly can. However, one of your factors in the bottom, in the denominator, is an irreducible quadratic. Well, that sounds fancy. All that means is that it doesn't factor any further. So for example, if you had x plus 1, and then you had here x squared plus 3, well, this is linear, so that's fine. That's just a over x plus 1. But this, it doesn't factor any further, but it's not linear. It's still quadratic. So when it's quadratic, your partial fraction has to be of this format. It has to be a degree lower. So in the linear, a degree lower is just a number. That's why I'm just putting a single letter up there, and a, b, and c are just numbers. Well, and so this one, it would be a over x plus 1, because that one's linear. But then I would need, because this one's quadratic, I would need a bx plus c. This has to be 1 degree lower than that. So therefore, it's going to be bx plus c to account for the fact that this was quadratic and not linear. Now, again, the key here is you have to understand this has to be non-factorable. Students will say, oh, I did that. They'll have, let's say these are their factors, x plus 1, and then x squared minus 9. Right? That's x squared minus 9. And they'll say, oh, I put ax plus b or bx plus c over this one. So why did you do that? I said, well, I had a quadratic here. Yeah, but you didn't keep factoring it. It'll factor further into linears. So you only have to worry about this scenario here, which is important. You have to remember it. If this is non-factorable quadratic that you can't factor any further. And I have an example that shows you both of these. So that's where we're going to go next. Okay, so those last two are really, really important that you can try and make sure you pick them out. Don't worry about this part down here. It's just going to show you how to get your answer. So we'll put it all into play here in a couple of examples. Okay, let's take the first one. I end up doing these on separate pages, so I'm just going to move this to a new page. Okay, so the first thing you're supposed to do is factor these as far as possible. This will factor again, and it will factor down to the integral of x minus 1 x. This is x plus 1, it's a perfect square trinomial, so it's x plus 1 squared. Big flashing red light should go off here. linear repeated factor. That was note 3, I think it was on that last slide. So I got to make sure when I set this up, I account for that. Here we go. I'm just going to ignore the intervals for a little bit when I do my partial fraction work, and I'm going to figure out what's another way to write this expression. So we're going to take, because it's this repeated one, so I've got a over x, that's no big deal, plus b over x plus 1 squared, plus c could be over just x plus 1 to the first, because x plus 1 squared is a common factor or denominator for this as well. And I want to make that equal to x minus 1 over x onto x plus 1 squared. Now, essentially, as you get a little bit more comfortable with these, you can, for all intents and purposes, get rid of your denominators because, put it here, this, and this, if you get the common denominator, this is what students will do wrong. They'll say, oh, you multiply the 3 together. No, that's not how you necessarily get the least common denominator. In this case, x I need, yes, but because of these two, you only need an x plus 1 squared. That covers this one and this one, which is now the same as this. And that's what you want. You want the denominator here and the denominator here to be the same. Well, in order to get this denominator, the first one, the a, I would have to multiply that by x plus 1 squared. The b would only have to get multiplied by x, and it would have this would become this. This one, the c, I'd have to multiply by x to get the x. I have x plus 1, but I want x plus 1 squared, so I'd have to also multiply it by an x plus 1. So if you multiply this fraction by those two, you'd get that denominator. If you multiply this fraction by just x, you'd get that denominator. If you multiply this fraction by x plus 1 squared, you'd get that denominator. And I want the numerators now, because the denominators are already equal, at this point we say, okay, what is going to happen here in order for these numerators to be equal? So we're going to start expanding things out. A onto x squared plus 2x plus 1 plus bx plus cx squared plus cx. That's eventually going to have to equal x minus 1. Bring the a into these brackets. I'm going to get ax squared plus 2ax plus a plus bx plus cx squared plus cx equals x minus 1. So this, you want this to be all expanded out, added and subtracted. This one's all addition and equal to the numerator of the right side. Now, at this point, what I like to do is do them in order, because I like to have a pattern. So I always start with the highest exponents and work my way down. So let's start with the x squareds. I've got a in front of this x squared, and I've got c in front of this x squared. And if you look over here, what do you got for x squareds? I don't have any x squareds, which tells me then that when I take the a, the number in front of this x squared, and I add it to the number in front of that x squared, I need to get 0. There's one equation. Okay, let's do the x's. 2a, so the number in front of that x, plus b, plus c, has to equal the number in front of the x here, which is a 1. And then last but not least, anything that doesn't have a variable attached to it would be your numeric term. So I have an a, and that's the only one. That's always nice when that happens. So that means that a has to be equal to the numeric term over here. There, we got one of the letters already. So then you're going to look over your equations and say, well, what should I get next? Well, I suggest we go here. Let's go here because I know a now. So -1 plus c's got to be 0. Well, c's got to be 1. So now I know a and I know c. I can go to this equation and figure out b. So twice a, so twice a plus b plus c has got to give me 1. This is -2 plus 1, so b minus 1 has to equal 1, so b's got to be 2. And you got to be careful to make sure you put these in the right place. So I'm going to go up top here, I'll scroll up for a second and say, okay, what's a over? A is the 1 over the x. So it is, and remember, I'm just taking the original question, there's the original question, and I'm rewriting it in this form instead. Okay, so a is -1. So it's the new question. The new question is the integral of -1 over x dx plus b, which is 2, and d is over the x plus 1 squared. So the 2 plus the integral of 2 over x plus 1 squared dx. And then finally, c, I think it was just over x plus 1, and c, I think c is just 1. So c, it was c over the single x plus 1 not squared dx. And then hopefully you now have integrals here that you can manage. Well, the first one's easy. It's du over u, so it's natural log. This one is a chain rule. And this one's another natural log. So I've got -1 integral of 1 over x dx. 1 over u du, that's natural log. Plus 2 integral x plus 1. I just bumped that up to the numerator, made it -2 dx. This is chain rule. Something in brackets, 2 an exponent. The derivative in the brackets is a 1, so that's obviously there. I'll undo that chain rule. And then I've got integral here of 1 over u. Derivative of this would just be 1, so it's du over u. We're set to go. The first one would be -1. I don't need that form. It's just negative natural log of x. This one, I'm going to add 1 to the exponent, so it's going to go to -1. Divide by -1 is going to switch that to -2. Natural log. Try that again. It's chain rule. Add 1 to the exponent, it's going to be -1. Divide by the new exponent, it's going to be -2 on the x plus 1 to the -1. This one is now also du over u, so it is a natural log of x plus 1 plus c. I know we talked about this way back, probably even before we went on our extended break. Sometimes you'll notice I'm putting these absolute value on there, and that's just to guarantee, because we can't take the log to any base of negative arguments. So that's just a way to guarantee that you don't put something in there that will give you a negative argument. Okay, so that's why you'll notice that I put those absolute values on the natural logs. So you don't always, you're right, I don't always, because sometimes it's been something like this. Let's say it was the natural log of x squared plus 4. No, I don't need absolute value because there's no way that could ever be negative. If you put a negative in here and squared, it's still going to be positive. So in this case, no, I don't need absolute value bars. That's why sometimes there is and sometimes there isn't. Okay, one more example, and then I'll let you try your luck at these ones. Well, they kindly at least factored the denominator all out for us. We've got a linear. This does not factor. So this is a non-factorable quadratic. Let's build the partial fractions. So the partial fractions would be a over x minus 2 plus, now remember, if it's non-factorable quadratic, you need your numerator to have an x in it, 1 degree lower than this. So it's going to be bx, but then you're also going to need a numeric term that could possibly be there, bx plus c. And that's because this is non-factorable quadratic. And that's going to equal the right side, which is 2x squared plus x plus 16 over the denominator. Get a common denominator here, which is these two multiplied together. First one I'd have to multiply by x squared plus 9. The second fraction, the whole thing, put it in brackets. You would have to multiply it by x subtract 2. That's going to keep coming down here. I have to rewrite it all the time. Then I'm going to expand the numerator. The numerator is ax squared plus 9a plus, this is binomial by binomial, so bx squared, subtract 2bx plus cx, subtract 2c, and this is the numerator. Right, this is still over x minus 2 onto x squared plus 9 equals, that's still here. Denominator and denominator are the same, so this has to equal the numerator of this, which is what you always end up doing. At the very end, it's setting numerator equal to numerator, assuming you've got your common denominators properly. So let's do that. Okay, let's do x squareds first. So I have a plus b, a plus b, has to equal the x squared term in the numerator at equal 2. So a plus b has got to be 2. Let's do the x terms. I got a negative 2b in front of this one and a plus c in front of this one. So when I combine those coefficients, I have to get the coefficient of the x term in my final answer, which is 1. Right here, a 1. So that one's got to equal 1. And then I have to do my numeric terms. So I've got a 9a and a minus 2c. So 9a subtract 2c has to equal your numeric term, which is equal to, right here, there's your numeric term, a positive 16. Okay, well this one's going to involve some more difficult system work. Let's suppose I take this one. So you're going to have to do some substitution here. Elimination is not going to work because they're all different letters on the go in them. Let's take this top one and get the substitution for A. A is really 2 minus B. Right? That's that equation just rewritten. I'm going to put this in here where the A is. You say, well, why would you do that? I'm going to do that because that'll make this equation have B's and C's only, and this equation will have B's and C's, and then I'll be able to work with this system over here. So I'm going to take 2 minus B and put it in for the A. So it's 9 onto 2 minus B, take away 2C, has to equal 16. So 18, take away 9B, take away 2C, has to equal 16. Negative 9B, subtract 2C, bring your 18 over, it's going to equal minus 2. I don't like all those negatives, so why don't we just divide everything by negative 1. And I've got 9B plus 2C equals a positive 2. Line that up with this one. Negative 2B plus C equals 1. And now I've got two equations with the same two variables on the go. So I'm going to, you get substitute, you get C equals 1 plus 2B and put it in here. Let's keep it going that way this time. So let's take this equation right here and write it as C equals 1 plus 2B. So 1 plus 2B is going in here. So it's going to be 9B plus 2. Instead of C, we're going to put 1 plus 2B in its place. And I'm going to have 9B plus 2 plus 4B equals 2. 9B plus 4B, 13B. Oh, look at this. 2 take away 2 is 0. That means B's got to be 0. Which is fine. That'll happen. Okay, let's get C next then. C is 1 plus 2B. So C is 1 plus twice the answer I got for B, which is 0. So C's got to be 1. One more to go. Let's see. So I need an equation. Let's go with the one with A and C. All right, let's go with this one even. A is 2 minus B. So A is 2 minus B. Well, A's got to be 2. So there's, again, that's pretty labor intensive, but it's fairly structured, and as long as you can solve systems of equations, which is a skill we would have done in our pre-calc streams. Okay, let's rewrite the original question. So A, if I go back up here, A was what was over x minus 2. So A is 2. So it's the integral of 2 over x minus 2 dx plus B was 0. That's nice because that's going to make this next one a bit easier because that's right here. Look, so B is 0. So that means there's no x term. You're just going to get your C, which I believe was a 1. C is 1. So now it's the integral of just 1c. So b was 0. So 0x plus c. C was 1 over x squared plus 9 dx. Now this natural log, not natural log. Trig substitution. Just to give us some more practice, we got to set up a trig substitution. So remember, this is all one question. So often a question like this, you'll see them valued at like 10, 12 marks just because there's so much work to do these. I'd want x and 3 to be my two sides. This would be x squared plus 9. Take the square root of it. Pick an angle theta. Let's go tan of theta is x over 3. 3 tan of theta is x. Take the derivative of both sides. 3 secant squared theta d theta would equal dx. So there's my substitution for dx. I need something for this, so I want this side and this side. Secant theta. Secant theta would be the square root of x squared plus 9 over 3. So 3 secant theta is the square root of that. I don't want the square root on it, so I square both sides. All right, so my integral that I have up here still left to do, the one that I couldn't tell just by looking at it, is going to be integral dx is 3 secant squared theta d theta. X squared plus 9 is 9 secant squared theta. Those are gone, those are gone. I'm going to get 1/3 integral of d theta, which is 1/3 theta. So that's the integral of this one. So let's put it all back together here now. And instead of theta, I'm going to put inverse tan of x over 3. Integral of, no, sorry, I'm going to do the integral of that. So it's going to be natural log, so 2 natural log x subtract 2 plus 1/3 instead of theta. I'm going to go with inverse tan of x over 3 plus some constant c. Now, I'm just going to show you something here. This will be the last thing I'm going to show you about integration. Is all of this work here. Sometimes if you get fairly clever with this, you can avoid that. And when you can do that is when you look at this pattern here, if that was x squared plus 1, this would be really easy because it would be inverse tan perfectly. But it's not plus 1, it's plus 9. So I'm just going to show you, I'll do it on a clean slide here. If I had the integral of dx over x squared plus 9, I'm going to do this without actually drawing the triangle doing the trig substitution. Here's a little trick you can use. If you have inverse tan of u, the derivative is du over u squared, u squared plus 1. So this is close if u was x, right? Du would be 1. This would be u squared, but this is the wrong number. Well, you can fix that by factoring. And the way you do it is you take the integral of dx and you factor out, there's a 1 in front of this one, you factor out a 9. And the reason you factor it in 9 is because that'll make this become 1. And then this would become 1 over 9 x squared plus 1. Bring your 1/9 to the front. Then you've got dx over, I'm going to write this as 1/3 of x squared, u squared, that would give you that. So then the only thing you're missing is that, well, du has got to be a 1/3. So if you multiply by 1/3 here, that means you've got to multiply also. So if you multiply there by 1/3, you've got to multiply here by 1/3. Now, this is going to be like this though, so we're going to get, oh, sorry, let me back up for a second. So my 1/3 and 1/9, that's 1/27. Why I was putting it over 1 doesn't make sense. Then I've got the pattern here, du over u squared plus 1. I want the integral of that, so that's inverse tan. And u would be 1/3 of x plus c. What? I messed up the constant, but not in front. I'll go back here for a second. So I get it out the long way with the triangle. I got 1 over 9 inverse tan of x over 3. What? I got 1 over 27, so I messed up my constant. Let me just double check this constant. This is why I don't do it this way. I like drawing the triangles, but you may see someone do it this way next year, so I want you to at least see an example. When I put a 1/3 there, I got a 1/9. So that 9 is in the bottom. That 1/3, oh, that's why. Because the 1/3, I'm multiplying the numerator by, so I got to multiply. Let me just back up here for a second. So right here, my 1/3. Right, so the problem was, the problem was, when I put the 1/3 there, I should have multiplied the denominator by 1/3, not the numerator. So now it should be 1 over 1/3 of 9 is 3. And then this is what we just, not an integral anymore. We're going to do the integral. So it's going to be 1/3. Now it's this pattern. So that's inverse tangent of x over 3, or 1/3 x. So there's a way to do it without actually doing the trig substitution. That one was a little rough. Let me just kind of show you that again, quick and smooth. So let's suppose I had dx over x squared plus 25. So rather than drawing out the triangle, I'm going to take out 25 as a GCF. So dx 25, 1 over 25 x squared plus 1, which is the same thing as having dx. Bring your 1/25 out front. This is 1/5 x squared plus 1. The du here is 1/5, which means I got to multiply the denominator by 1/5, which would make my answer 1/5 inverse tan of 1/5 x plus c. Once you get the hang of it, it's actually a pretty slick little way to do it without the trig substitution. All right, that finishes up all of our techniques of integration. That is the last of new material that I am going to put on your plates for this school year. The remainder of our time, which is still significant, is going to be spent on getting better at integration. So you're going to be thrown now random sets of problems. Some I'll collect, some are just to practice, but they're going to be mixed matches of all the different strategies of integration. And you're going to have to try and integrate those. Now, before I get to that though, I am going to give you just in the practice in your class notebooks, you will find a couple of examples of just partial fractions where you can practice today's new strategy and just make sure you've got that down before we start mixing and matching. All right, best of luck with that.